In Yellowstone National Park, geologists say one of the park's famous geyser basins now has a new hot spring.
The United States Geological Survey, USGS, has issued a rare and urgent red alert following the sudden emergence of a disturbing geological phenomenon beneath the Appalachian Mountains. This alert, the most severe warning the agency can issue, comes amid the detection of massive subterranean shifts and unexplained seismic activity deep beneath one of North America's oldest mountain ranges. Scientists monitoring the region's geophysical systems have been observing a series of increasingly unusual and alarming data points that suggest something profoundly significant and potentially catastrophic is occurring far below the surface. Before we start, smash the like and subscribe buttons for more updates. The initial signs began subtly. Seismic sensors embedded in the bedrock of the Appalachians, which typically detect only low-level tremors due to the mountain range's ancient and stable geology, started registering low-frequency vibrations. At first, these tremors were sporadic and mild, barely above background noise, but over the course of several weeks, they grew more intense and consistent. What stood out to scientists wasn't just the strength or frequency of the tremors, but their pattern. These were not typical seismic events caused by tectonic plate movement or fault line slippage. Instead, they carried a resonance, deep pulsing waves, indicating that whatever was occurring was not just geological, but possibly magmatic or even more complex. Satellite imaging corroborated the unsettling findings. Thermal anomalies began to appear along a swath of the Appalachian Range, stretching from northern Georgia through western North Carolina and into eastern Tennessee. Infrared scans showed areas where the ground temperature had risen several degrees Fahrenheit above average, with some hotspots emerging near seemingly inactive fault lines and long-dormant volcanic features buried beneath the thick forest canopy. The combination of deep harmonic tremors and surface thermal readings prompted the USGS to elevate its watch level, and when further scans revealed rapid deformation of rock layers more than 10 miles beneath the surface, the red alert was issued. What is particularly disturbing about this event is the geological context of the Appalachian Mountains themselves. Unlike the younger and more volatile Rockies or the Pacific coastal ranges, the Appalachians are considered a passive, eroded system, one that hasn't seen significant volcanic or seismic activity in millions of years. Their roots go back over 480 million years, to the time of the supercontinent Pangaea. Their slow weathering has created a landscape rich in biodiversity and cultural history, but not typically associated with urgent geologic risk. That makes the current activity not only surprising, but difficult to classify using known geological models. Deep Earth monitoring stations have since detected the migration of what appears to be a large plume of partially molten rock, magma, rising from the mantle. This mantle plume is unprecedented in its location. Previous modeling of the North American plate had never indicated the possibility of such activity beneath the Appalachians. Yet the data is undeniable. Seismic tomography now shows a defined column of superheated material moving upward, fracturing ancient rock formations and displacing massive volumes of subsurface material. This movement is also producing bursts of high-energy acoustic emissions, which some experts have compared to the geological equivalent of roaring, a sound previously only recorded in volcanic regions just before major eruptions. Adding to the concern is the speed at which the situation has evolved. Geological processes often move at glacial paces, but this plume's ascent seems to be accelerating. In less than 2 weeks, it has risen several kilometers, and the deformation it causes is becoming visible even at the surface in certain areas. Forested hills are subtly bulging, and in remote areas of North Carolina, small fissures have begun to open, releasing sulfurous gases that suggest chemical reactions between magma and groundwater. These fissures, while not yet wide or deep, are unusual for the region and signal a shift in subsurface pressure dynamics that experts are struggling to model accurately. Compounding the mystery, GPS stations atop various Appalachian peaks have recorded micro-tilting of the terrain. These stations, which are designed to detect millimeter-scale shifts over long periods, have registered consistent lateral and vertical movements inconsistent with natural erosion or tectonic drift. The data shows uplift and distortion patterns eerily similar to those observed prior to the formation of surface calderas in active volcanic zones, such as Yellowstone. Yet, unlike Yellowstone, the Appalachians have no known magma chamber until now. The emerging picture is one of a geologic force that has lain dormant for millions of years, suddenly awakening, as if stirred by some unknown catalyst. The implications of this awakening are staggering. Should the magma plume continue to rise, it could culminate in the formation of a new volcanic structure, or worse, a series of hydrothermal explosions and phreatic eruptions as superheated rock contacts underground aquifers. Given the densely forested and populated nature of the Appalachian region, even a moderate eruption could have devastating consequences. Towns nestled in the valleys, places like Asheville, Boone, and Roanoke, sit directly within zones that may be impacted by pyroclastic flows, ashfall, or ground subsidence. Scientists are working around the clock to install more sensors, run simulations, and understand the scale of the emerging threat. At the forefront of these efforts is a multidisciplinary task force involving geophysicists, volcanologists, atmospheric scientists, and emergency response coordinators. Data modeling is being pushed to its limits. One of the most concerning hypotheses is that this event might be tied to deeper mantle instabilities that could affect not just the Appalachians, but possibly initiate seismic chain reactions along the eastern seaboard. Some simulations even propose that this plume could connect to ancient buried rift zones that stretch beneath the continent, meaning the activity might not be localized, but part of a much larger geodynamic shift. The sudden emergence of this anomaly is also forcing a re-examination of previously held assumptions about the interior structure of the Appalachian region. For decades, it was believed that the crust here was too thick and cool to permit mantle plumes to ascend. However, new evidence suggests the presence of a weakened lithospheric zone, perhaps the result of ancient tectonic collisions or long-term chemical weathering, that has opened a vertical path for magma movement. This raises uncomfortable questions about what other presumed stable regions might also be vulnerable to similar events. Another layer of complexity is being added by electromagnetic anomalies. Instruments have begun detecting low-frequency electromagnetic pulses in conjunction with the seismic and acoustic activity. These pulses, though not fully understood, are believed to originate from the interaction of moving magma and mineral-rich crustal layers. In some cases, they've even interfered with GPS and communication systems in isolated patches along the mountain range. The cause and full extent of these pulses remain under investigation, but they add another indicator that the geological dynamics at play are more multifaceted than initially thought. Local wildlife has also begun to react. Biologists and park rangers across multiple national forests have reported widespread disruptions in animal behavior. Birds are migrating prematurely. Deer and elk have been seen fleeing their usual territories, often in the middle of the day. Insects that are sensitive to underground vibrations, such as cicadas and ants, have altered their nesting and emergence cycles. Some areas are experiencing mass die-offs of fish and amphibians near freshwater springs, suggesting chemical contamination possibly linked to escaping subterranean gases. While anecdotal in isolation, taken together, these ecological signs suggest that nature itself is responding to the changing subterranean conditions. The potential environmental impact of a full-scale geological awakening in the Appalachians would be vast. Besides the direct danger posed by volcanic or seismic activity, secondary effects could include atmospheric disruption from ash, widespread forest fires triggered by heat and gas emissions, and contamination of freshwater sources. The Appalachian region is home to one of the most diverse temperate forests on Earth, with ecosystems that have developed undisturbed for millennia. Any long-term disturbance from geothermal shifts could irreparably damage these habitats, triggering a cascade of ecological changes with far-reaching consequences for the broader eastern United States. Infrastructure vulnerability is another rising concern. The Appalachian region, while rich in natural beauty, also hosts a dense network of roadways, tunnels, and pipelines that were never constructed with volcanic or high seismic activity in mind. Bridges, rail lines, and older dams may be especially susceptible to ground deformation and microfracturing. Emergency preparedness measures are being reviewed, and contingency plans are being drawn up, but the region's historical lack of geologic volatility means it is under-equipped to handle the rapid escalation of events. Geopolitically, this red alert has caught many by surprise. Energy corridors, communication hubs, and even military installations are located in or near the Appalachian Zone. A significant geologic event could compromise key infrastructure and force rerouting of critical services. National agencies are now coordinating to model not just the physical risks, but also the socio-economic ramifications of a potential disaster scenario. Insurance markets have already begun adjusting for risk in the southeastern United States, and emergency drills are being conducted in counties that until now had no known history of geologic hazards. The deeper story unfolding beneath the Appalachian Mountains may also reshape scientific understanding of the Earth's interior. The current theories of plate tectonics, mantle convection, and continental stability are being put to the test. Researchers are calling for new models that account for reawakened zones, areas previously thought to be tectonically inert that may, under certain conditions, become active again. This calls into question the predictability of long-term geological behavior and raises the possibility that many of the world's so-called stable regions may not be so immutable after all. As the mantle plume continues its ominous ascent, uncertainty remains the dominant feature of the unfolding event. The situation is dynamic and evolving faster than anyone had anticipated. Scientists are scrambling to make sense of it, using every tool at their disposal, from satellite imaging and borehole thermography to experimental AI-based seismic analysis systems. Yet despite the influx of data, the full scope and trajectory of the threat remains unclear. What is certain is that the red alert is not symbolic. It reflects the highest level of geological concern the USGS can express, and its issuance signals that the country may be on the brink of an event unlike any in recent memory. The ground beneath the Appalachians, long regarded as quiet and unchanging, has spoken. What it's saying is not yet fully understood, but the message is urgent, the signs are growing, and the implications reach far beyond the mountains themselves. A force long dormant is rising from the depths, ancient and unstoppable, challenging the very idea of geological stability. The coming days and weeks will determine whether it remains a curiosity of nature or erupts into a historic reckoning with the raw power of the Earth. The red alert issued by the USGS has triggered an extraordinary mobilization of resources, as institutions across the country pivot to focus on the rapidly developing situation beneath the Appalachian Mountains. The urgency of the alert has spurred not only scientific curiosity, but also a tangible sense of dread, as early indicators suggest that the unfolding event could herald a tectonic transformation unlike anything seen in this part of the world in recorded history. The Department of Energy has entered the scene to assess the potential impact on underground fuel and gas storage systems that lie in the vicinity of the activity. The Appalachians are crisscrossed with legacy pipelines, abandoned coal mines, and vast natural gas reserves, some of which are stored under pressure in geological formations. Any significant geological shift could rupture these containment systems, creating scenarios where gas leaks lead to explosions or underground fires. In a worst-case scenario, disturbed subterranean gas pockets could ignite due to the proximity of superheated materials, resulting in chain reactions that would be nearly impossible to contain. Meanwhile, hydrologists are expressing alarm over the potential effects on the region's vast aquifer networks. The Appalachians serve as a critical water source for millions of people across the eastern United States. Aquifers run beneath the range like subterranean arteries, feeding into springs, rivers, and lakes across multiple states. Rising magma, even without breaching the surface, has the potential to superheat these underground water channels, causing flash boiling and pressure accumulation that could erupt as geysers or mud volcanoes. Furthermore, the chemical interaction between magma and groundwater may release hazardous compounds such as hydrogen sulfide and hydrochloric acid, potentially contaminating entire freshwater systems. Further complicating matters is the unknown nature of the underlying rock composition deep beneath the Central Appalachians. Much of what lies at the depths currently affected has never been directly sampled. Geologists are now racing to analyze core samples taken from decades-old drilling projects to reconstruct the deep subsurface profile. Early speculation suggests that certain layers may contain volatile elements, such as pockets of compressed methane clathrates or mineral deposits prone to exothermic reactions, that could magnify the energy release from any intrusion of heat or pressure. if even a portion of these deposits were to be destabilized. The resulting explosion could rival some of the largest non-nuclear blasts in history. At several national laboratories, advanced computer simulations are being developed to map the propagation of stress and heat through the crust. These simulations incorporate real-time satellite telemetry, seismic wave data, and historical geological records. Initial outputs are not encouraging. The pressure vectors show a worrying trend. The plume appears to be branching laterally as well as vertically, following pathways of least resistance. This pattern mirrors the kind of complex intrusion networks found in rift zones or beneath active calderas. It raises the possibility that instead of a single centralized eruption point, multiple vents could form, distributing the energy across a wider region and complicating mitigation or containment efforts. At the same time, atmospheric scientists are beginning to monitor for early signs of gas seepage into the air. Elevated levels of radon have already been detected at several monitoring stations. Radon, a naturally radioactive gas, often serves as a precursor signal of deeper geological unrest. Its sudden appearance in higher than normal concentrations is both a health risk and a red flag. More troublingly, sensors are beginning to pick up traces of carbon dioxide and sulfur dioxide, both indicators of magmatic activity. In some cases, these gases are being released in areas not previously associated with faulting or geothermal activity, which implies that the underlying system is expanding or fracturing new pathways to the surface. Amid all this, atmospheric anomalies are becoming more apparent. Strange cloud formations, sudden shifts in barometric pressure, and localized temperature drops have been reported across parts of Virginia and West Virginia. These microclimate effects may be a result of gases rising invisibly into the atmosphere, where they influence weather dynamics in real time. Certain types of volcanic gases, when released in large volumes, can seed cloud formation, alter wind patterns, and even produce high-altitude lightning through ionization processes. Such occurrences, while not yet fully confirmed, would provide further evidence of escalating subterranean activity. Interestingly, the ongoing geological developments are having an unexpected impact on magnetic field measurements across the region. Magnetometers placed near affected zones have started to record subtle yet persistent deviations from their baseline values. These anomalies, though still under study, may suggest movement of ferromagnetic materials underground or changes in the Earth's magnetic flux caused by thermal gradients and mineral displacement. While not immediately dangerous, such changes can disrupt navigation systems, affect wildlife migration, and interfere with sensitive equipment used in everything from aviation to power grid management. In response, the USGS has begun expanding its network of mobile geosensing units, autonomous stations capable of recording seismic, thermal, atmospheric, and chemical data simultaneously. These mobile units are being deployed across the Appalachian corridor and are feeding real-time information into a national coordination center. This center now operates 24 hours a day, staffed by a rotating team of geologists, emergency analysts, and public safety officials. Drones equipped with LiDAR and hyperspectral imaging systems have also been dispatched to map terrain changes and detect subtle shifts in elevation or vegetation stress that may signal hidden faults or underground gas pockets. While much of the focus has been on the physical consequences, the psychological and sociological effects are beginning to mount as well. Communities situated along the Appalachian Range, many of them rural and tightly knit, are grappling with the slow-building tension of a possible disaster that defies conventional preparedness models. Unlike hurricanes or floods where forecasts provide clear windows of impact, this unfolding event is nebulous, slow-burning, and without precedent. People are watching the ground beneath their feet change, unsure whether it will continue to shift quietly or erupt with cataclysmic force. Emergency management agencies have begun issuing advisories, even while acknowledging they lack a historical template to follow. Evacuation protocols are being drafted for areas where ground deformation is most pronounced. Schools and municipal buildings are being assessed for seismic stability, and emergency broadcast systems are undergoing updates to handle a potential multi-state alert. Medical facilities are being asked to conduct readiness checks, with a special focus on respiratory support capabilities in case of airborne particulate release from ash or gas. What makes this situation uniquely unsettling is how little precedent there is to draw upon. the eastern United States has no living memory of significant volcanic activity. The perception of the Appalachian Mountains as immutable and tranquil has been reinforced for generations, but this perception may have lulled policymakers and planners into a false sense of security. Now that legacy of assumed stability is being shattered, and institutions must pivot swiftly to address risks they were never designed to accommodate. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on the USGS Red Alert beneath the Appalachian Mountains? We want to hear from you. Thank you for watching and see you next time.